So the talk is going to be about leverage scores, and I think this session is going to be considerably more technical. What are leverage scores, first of all? Leverage scores are a statistic on the rows and the columns of a matrix, and they reveal influential rows and columns in a matrix. What do I mean by influential? I mean rows and columns that, for example, if you pick them, you're going to get good approximations to the singular vectors and singular values of the matrix. We'll make all this precise during the talk. Now, the leverage scores are going to be a statistic, and in the algorithms that I'm going to describe, they're going to be used as a sampling probability. So instead of keeping, for example, rows and columns with high leverage scores, we're going to sample with probability proportional to the leverage scores. And we'll see that this very simple strategy will give some good results for a number of interesting problems. So my talk will have three parts. First of all, I'm going to show you how leverage scores are useful in the context of regression problems. And I'm going to look at a very simple case of regression, just L2 regression least squares problems. And this is where I'm going to formally define the leverage scores. It's going to take me a few slides, so bear with me there. Then I'm going to discuss how leverage scores can be used in the context of the column subset selection problem, where you want to really do feature selection. You want to pick a subset of columns from a matrix, or rows, it doesn't matter, just work with the transpose of the matrix, that contain good information about the matrix, again in the sense that I will make precise. And finally, I'm going to make a connection between leverage scores and the notion of effective resistances. Those of you yesterday at Fan Chang's talk saw the notion of effective resistances. They've been used to solve systems of linear equations with Laplacian matrices as inputs. We're going to see that the leverage scores are essentially equivalent to the effective resistances in that particular setting. So let me start with regression, just to make sure we're all on the same page. This is the problem I'm looking at. I'm trying to minimize ax minus b, the Euclidean norm of that. Notice that this is basically a vector. A is my design matrix, if you want. So the rows of A define the constraints on my problem. X is the vector of variables, and B are the measurements. I'm going to be looking at the over-constrained case. So I have way more constraints than variables. If you want, in matrix language, if this is an n by d matrix, n is larger, considerably larger than d. Under constraint can be handled in a very similar way. I'm not going to discuss that, but I'm happy to give pointers offline if somebody's interested. The square case is different. The square case in regression, of course, is basically boiling down to solving a system of linear equations. We'll get back to that at the end of the talk. So in the beginning, we're looking at over constraint. And again, under constraint is pretty similar. In this particular setting, there is typically no solution vector x such that ax is equal to b. So we're trying to just get the best fit that minimizes ax minus b. And as I said, I'm looking at the simplest norm, the Euclidean norm. And of course, we know a lot about this problem. We know how to solve this exactly. And you're looking at a few methods here that solve the problem exactly. And you're going from less numerically stable to more numerically stable. So you can solve the normal equations using, for example, Cholesky factorization. You can do a thin QR decomposition in the particular setting that I'm looking at. Or you can use the singular value decomposition. If you don't know what the SVD is, I'll get back to formal definition a few slides later. But what I want to mention here is that all these methods have essentially the same asymptotic complexity, but you're getting more and more numerically stable as you move down. Well, you pay a penalty for this, and the penalty is that this order nd square complexity, it's nd square because it's linear on the large dimension, which is n, and quadratic on the smaller dimension. The penalty that you pay, is that the constant factor increases. And we have a closed form solution for the least squares regression. It is the optimal vector x hat is equal to a plus the pseudo-inverse of A times B. If you don't know the pseudo-inverse, it's just a generalization of the inverse in cases where the matrix is non-square, as is the case here, or the matrix is not full rank. And of course, you know the actual value of the residual is basically the part of the vector, the norm of the part of the vector of the target vector B that lies outside the column space of A. So we know all this, we know how to solve this exactly, order nd square time, and so on and so forth. What am I going to be doing? First of all, let me give a pointer to something that actually Michael will be talking about in the next talk, which is that there are ways to approximately, randomized algorithms, to approximately solve L2 regression faster than exact methods. And those methods actually have been parallelized. They started with a very nice idea by Thomas Sarlos, who is actually here, in Fox in 2006, and then we had a follow-up paper in New Math a few years later, where the idea was to pre-process the input matrix A by using random projections, and then solve an induced smaller problem. What I'm going to focus on in this particular talk is the existence of corsets for L2 regression. What is a corset? I want to pick a subset of the constraints. So instead of looking at all the constraints, I want to pick just a subset of the constraints and solve the problem only on that subset of constraints. And it's not immediately obvious how many such constraints you should pick, or if there is an easy algorithm to pick those constraints. So here is the formulation. This is my original problem. I'm going to come up with a set of probabilities. Those are going to be my leverage scores for the constraints, for the rows of the matrix A, and of course for the elements of B. Actually, these probabilities are going to be agnostic on B, which is quite interesting. So I'm going to come up with a set of probabilities, and here's what I'm going to do. For every row of A, I'm going to flip a coin, and if that particular row is associated with probability Pi, I'm going to keep the row with probability R times Pi. And this is just a technicality to make sure that this probability does not exceed 1. If it exceeds 1, just pick that row. And so I'm going to select a subset of rows. I'm going to form a smaller problem and solve that problem. This is one sampling strategy. We'll see a slightly different sampling strategy a bit later, and it doesn't really matter. Notice that this sampling strategy guarantees that a row will be picked at most once. It will either be picked or it will be ignored. How many rows am I going to keep? In expectation, I'm going to keep R rows. And you can do measure concentration and show that with high probability you're going to be pretty close to keeping R rows. So I start with the original problem. I fix a set of probabilities which I have not revealed yet, and those probabilities are going to be the leverage scores, and I form an induced subproblem. I solve the induced subproblem. Let's see what do we gain. This is one result, and it's coming from a paper that Michael Mahoney, Mutu, and myself wrote a few years back. And the idea is that if you take the induced solution, so the solution of your smaller problem, and plug it back into the original problem, what are you going to get? So you plug it in back to the original problem, which is typically what you want to do in applications. And of course, you are not going to be better than the optimal solution. There is no way to do that. So you are not going to beat the optimal residual, but you're going to be pretty close to that. So 1 plus epsilon close. It's a randomized algorithm. You're doing sampling, so you'll pay a failure probability, delta. And the important thing is what should be the right value of R. Again, I have not revealed the structure of the probabilities yet, but the right value of R is basically d log d. It's an n by d matrix, so d is the thin dimension of the matrix. D log d, log 1 over delta, that's the penalty you pay because you are doing sampling, over epsilon squared. So you basically need, if you forget about the log factors, d over epsilon squared, well, you do need the extra log d factor, and we can actually get rid of that, but I'll talk about that a little bit later. If you're wondering why am I not comparing x hat s, the solution to the induced problem, to the solution of the original problem, we actually have that. I'm just not showing the result right here. So we've done a number of those. There are a number of additional results you can get. Let me reveal the probabilities, which is what I really want to talk about here. First of all, I need to make sure we all know the singular value decomposition. You have a matrix A. You can break it up as U sigma V transpose. Sigma is the matrix of singular values. It is diagonal. And by convention, I have the largest singular value here, the smallest one down here. Notice that I'm going for a form of the SVD where I'm looking at the rank of the input matrix A. So this is a row by row matrix. These are the non-zero singular values, basically. This is the matrix of left singular vectors. The columns of this matrix are pairwise orthogonal and normal. These are the right singular vectors. The rows of V transpose are the right singular vectors. Again, the rows of V transpose are pairwise orthogonal and normal. And we can compute the SVD in basically time that is proportional to the longer dimension. So if m is, say, the long dimension, you are looking at mn squared time. Quadratic in the small dimension, linear in the large dimension. for the particular setting that I have in mind. My A is n by d, so this is what I'm looking at. This is the form of the singular value decomposition. Here's what's important. The columns of U are pairwise orthogonal and normal. What about the rows? You don't know much. What you do know is that the Euclidean norm of the rows of U are between 0 and 1. That's pretty much the only thing you can say. Those norms, the norms of the rows of U, are the leverage scores. So the probability distribution that is going to reveal to you which constraints are actually influential is this probability distribution here. The Euclidean norms of the rows of U, this is just a normalization factor. This beta is saying that you don't need to compute them exactly. Approximations will suffice as well. How much time do I need to compute the leverage scores? I need a lot of time. Order ND square. We'll come back to this point later, and David will have things to say about this. David Woodruff will have things to say about this in his talk as well. So these are the leverage scores. When we first came up with this probability distribution, we had no idea that they are called the leverage scores, but you give the talk long enough and somebody picks them up. They've been used in statistics for outlier detection. So what do? You take points that have high leverage scores and you discard them because they disproportionately influence the solution of a least squares regression problem. But if you believe that your data contain no outliers, that they're good data, then perhaps these are exactly the points that you want to pick. We'll come back to this when I show you some results on the real data set. It's important to note how much time we actually need. Again, I can compute them exactly by using the SVD, but that means that basically I have to spend a lot of time trying to figure out the leverage score, so this doesn't speed up the solution of least squares problems. And let me say that we need d log d over epsilon square constraints. If you are wondering what is the minimal size of a core set to get 1 plus epsilon approximations, we actually have answers to this problem, and this is joint work with my former student, Christos Boutsidis, he's now at IBM, and my colleague at RPI, Malik Magdum Ismail. Why leverage scores? What are they really doing? Well, it turns out that at the bottom of most of the proofs that we have, what you are actually arguing is that if you have an orthogonal matrix that is tall and thin, and you pick a subset of its rows using the leverage scores, what you are actually getting is basically another matrix that is almost orthogonal. And this result goes back quite a bit, goes back in time quite a bit, and it comes from approximating the product of matrices. I want to highlight that these days it's pretty easy to prove because we have a very nice machinery, matrix Chernoff and Bernstein bounds, and actually let me say that Ilse Ipson and her student Tom Wentworth have a very nice both empirical and theoretical evaluation explaining when you get approximately orthogonal matrices by sampling a subset of their rows in how tall and thin should those matrices be, what should those parameters be both in theory and in practice, and to the best of my knowledge these are the tightest bounds at this point. Okay, let me get to the second part. Column subset selection, another situation where leverage scores are of interest. The SVD takes a matrix A and approximates it by using a few left singular vectors, if you want to look at the low rank approximation, times another matrix X here, which has the corresponding singular values and the right singular vectors. In data analysis, this is an issue. This is an issue because the left singular vectors of a matrix are linear combinations of all the columns, so it is hard to interpret. So if you're doing data analysis, you are trying to reify left singular vectors, assign them a meaning, and the meaning might not be there. So a few years back, again with Michael and Mutu, we proposed an alternative decomposition, which is saying instead of looking at left singular vectors, look at columns from the matrix. So pick a subset of columns from the matrix, then form some other matrix X, and try to minimize A minus Cx. Now, interpretability is immediate. You're doing basically feature selection. Of course, you want a small c and you want a small error. What is easy, what is difficult? Coming up with a good x is easy. It's basically just the pseudo-inverse of c times a, so that's no big deal. The difficult part is the combinatorial optimization problem of picking a representative subset of columns. So pick c columns that basically capture the structure in your data. How do you do that? That's combinatorial optimization. It's actually a hard problem. Variants of this problem are NP-hard when k grows as a function of n, so you don't really, when c grows as a function of n, so you don't really expect to solve that exactly. This is called the count subset selection problem. It's been heavily studied in numerical linear algebra, especially when the error is with respect to the spectral norm and not the Frobenius norm. I want to show one theorem. This is a theorem coming from a paper with Michael and Muto a few years back. And it's saying that you can get A minus Cx, this is x, that is 1 plus epsilon close to the best you can do. So you can pick a subset of columns so that the Cx decomposition is 1 plus epsilon close to the best possible. You're never going to beat SVD. SVD has strong optimality properties. It's the best long-rank approximation you can get. How many columns are you going to keep? Well, approximately k log k over epsilon square columns. And here I made the failure probability a constant, so it's absorbed in the big O notation here. What's the algorithm? How do you pick the representative columns? Same story as before. This is actually a slightly different procedure for sampling. Instead of flipping a coin for each column, I could have done that. It also works. But here I'm just doing IID trials. So I'm sampling columns in C IID trials with replacement. This guarantees that I will sample exactly C columns, but I could sample a column potentially multiple times. So these are the two sampling procedures you could potentially use. Theoretically, they get the same results. Again, there are some differences, especially when you apply them in practice. It's the same story as before. It's a set of probabilities, again, leverage scores. And if you sample with probability proportional to the leverage scores, keep the columns that you sampled. This is going to be your matrix C. Then X is given by just the pseudo-inverse of C times A. You're done. Let's see the leverage scores again. You are looking at A sub k, the best rank A approximation to A. Now you're focusing on the right singular vectors on VK transpose. The rows of this matrix are pairwise orthogonal and normal. Great. The columns you don't know much, except that their Euclidean norms are between 0 and 1. So use the Euclidean norms of the columns of VK transpose, here they are, as your sampling probabilities. Those are again the leverage scores. The question comes, remember what I said. In statistics, leverage scores were mostly used for outlier detection. How do the leverage scores look in a real data set? And I picked a data set from a domain that I've been working on for over half a dozen years now, so I understand the properties of those data fairly well. And this is human genetics. In human genetics, here are the kind of data that you get. You take blood samples, you extract the DNA, and then you run it through SNP chips. So you basically genotype for many loci in the genome that are known to be polymorphic across humans. And you get matrices of this form. The rows are samples from various individuals. The columns are loci in the genome called single nucleotide polymorphisms. And what you need to keep in mind is that these days in modern studies, we're looking at thousands of individuals and we're looking at millions of SNPs. So I'm part of studies now that genotype 5 million SNPs. And we know that there are potentially over 10 million SNPs, such loci in the human genome. Not the whole human genome is polymorphic. I mean, most of it is identical across different individuals. So you get those matrices back, and even though those matrices look complicated and they contain genotypic data, reality is that for every SNP, because of the specific definition of a SNP, there are three choices. You can be homozygotic in one allele, homozygotic in the other allele, or heterozygotic. So this is basically a matrix of 0, +1, and -1. So you can encode this matrix very easily numerically. I'll show such a matrix through a picture. This is a data set that is fairly old, so you only have 270 individuals or so, 12 populations from around the world, about 10,000 SNPs, and this was back in 2005. These are the populations. As you can see, we have continental representation from Europe, Africa, Asia, and some Native American populations. This is what the matrix looks like. All the individuals are here. They are sorted by region. And these are the SNPs. There are three colors in this picture. Red, green, and black. Black corresponds to homozygotic, red and green to, black corresponds to heterozygotic, and red and green to homozygotic in either allele. These are the leverage scores of the columns of this matrix. Very non-uniform. Are these outliers? Are these things you want to discard from your data? Let's pull them out. So these are the top 30 SNPs with respect to leverage scores, and there are very clear structures that correlate with regions. This is unsupervised. I never told the leverage score computation algorithm what are the various regions. This is what I pulled out when I looked at the leverage scores that were outliers here, the top 30 basically, those marked with the star. As you can see, there are patterns in Africa, patterns in Europe, patterns in the Americas, no real pattern in Asia, but if you run k-means, with k equal to 4, you're going to get exactly the 4 clusters back. Now look at these SNPs. SNPs are loci in the genome, so we know a lot about SNPs. So if you look at the genes that correspond to those SNPs, you're going to see genes like the ones that are responsible for hair follicle formation or skin color, which are well known to differentiate individuals from different regions. So they have functionality, actually. So these are not outliers. These are actually important things that you want to pick out from your data. Okay, let me spend the last few minutes of my talk discussing the last application, which is an application of the leverage scores for solving systems of linear equations with graph Laplacians. And I need a few definitions. First of all, I'm going to look on weighted, undirected graphs. So undirected graphs, weighted, and the weights are going to be positive for a reason that will become obvious in a minute. The Laplacian matrix of G. You probably all have seen various definitions for the Laplacian. There is one very common definition. I'm going to use a slightly less common definition, which is that the Laplacian is the product of those three matrices. B transpose WB. Let me explain those matrices. W. It's a matrix of weights. M by M. There are M edges in the graph. This is a diagonal matrix, so everything off diagonal is 0. The weights are positive, so you can take the square root of this matrix. B is what is called the edge incidence matrix. You are looking at the rows of B. Each row corresponds to an edge. It's an M by N matrix. And it indicates the start and stop, the beginning and the end of every edge in the graph. Since there is no orientation, just arbitrarily pick an orientation and use a +1 to indicate the start, -1 to indicate the end of the edge. B transpose WB corresponds to the Laplacian. It's a symmetric positive definite matrix, so you can look at B transpose W to the half, B transpose W to the half, transpose, that's L. That's your Laplacian. One thing that I want you to keep in mind is that B is extremely sparse. It has 2 non-zero entries per row, so it has 2M non-zero entries. It's an M by N matrix, but extremely sparse. Effective resistances. If you think of a graph as an electrical network, you can basically say that every edge corresponds to a resistor, and the resistance of the resistor will be 1 over the weight of the edge. Then, to figure out what the effective resistance is of an edge, so the effective resistance between two vertices is basically a potential difference. You apply, if you want, a unit of current at one vertex, you extract at the other vertex, and you try to measure the potential difference. Well, there is also a mathematical formulation. It turns out that the effective resistances are the diagonal entries of this matrix here. B, that's my edge incidence matrix, the pseudo-inverse of L times B transpose. The reason you need the pseudo-inverse for the Laplacian is that the Laplacian is rank deficient, so you need to worry about this. What we argued with Michael a couple of years ago is that these effective resistances, the diagonal entries of this matrix, are exactly equal to the leverage scores of the matrix W to the half B. Up to scaling, but this really doesn't matter. So, effective resistances equivalent to leverage scores of this particular matrix that you can easily compute the matrix. Computing the effective resistances necessitates an SVD. Why do we care about effective resistances? The answer is that Dan Spillman and Nikhil Srivastava in Stock in 2008 argued that if you take a graph and you sparsify it by keeping only a few edges with probabilities proportional to the effective resistances, you get a sparser graph whose spectral properties are very similar to the original graph. Why is this nice? Because if you are solving a system of linear equations with a Laplacian matrix as input, you can use this sparsified graph as preconditioner. You actually can form a whole preconditioning chain, and it turns out that this allows you to solve systems of linear equations with Laplacian matrices as input in time that is basically linear in the number of non-zero entries in the matrix. A very nice breakthrough. How do you approximate effective resistances? I mean, this is useless if it takes a lot of time to approximate effective resistances. The original paper had a cyclical argument, so they were using their own solver to approximate effective resistances. Yannis Koutis, who is actually going to be giving a talk on Friday, along with Gary Mingler and Richard Peng, in a series of papers in the past few years, came up with a beautiful observation. Low stretch spanning trees provide natural approximations to effective resistances. And low stretch spanning trees are something that in theoretical computer science we know a lot about. They actually came up with a better algorithm to approximate low stretch spanning trees. And in this way, they were able to actually give a practical way of approximating effective resistances, which can be used later for graph classification. I'm sure that Yannis will talk about some of this work on Friday. An alternative way of working around this problem, I just told you that effective resistances are equivalent to leverage scores. Can we use the leverage scores, approximate the leverage scores, and sample with respect to those? Of course we could, but how fast can we approximate leverage scores? The original algorithm was basically, in this m by n setting, mn squared. This is useless. You can solve the system exactly in that much time. Along with a number of collaborators, Ken Clarkson, David Woodruff, Michael Mahoney, and Malik Magnum Ismail, we gave an algorithm which, for an arbitrary m by n matrix, can approximate leverage scores in time order mn and polylogarithmic factors. So it's better than the trivial, it's better than the obvious. Is that good enough for this setting, for solving systems of linear equations with Laplacian inputs? The answer is no. The reason it's not good enough is because the input matrix there only has 2m non-zero entries. The running time you are after is order m polylog m instead of order mn polylog m. So you need to get rid of this n. You basically want to approximate the leverage scores in time that is proportional to sparsity, not dimensions. And as far as we can tell, the algorithm we have here probably won't really be doing the trick. And it's time for me to conclude. So leverage scores, a statistic on rows counts of matrix that reveals, if you want, influential rows and counts in the matrix, equivalent to effective resistances for the setting of graph Laplacians. You can uniformize the leverage scores. Michael will talk a bit about this by preprocessing with random projection matrices. So you can get rid of the non-uniformities, but you have to precondition. And the open question is, how fast can we approximate the leverage scores for sparse matrices? I have a question mark here because I think David actually has answered this question, and I think that's what he's going to talk about in his talk later on. So thank you very much for your attention, and I'll be happy to take questions. So let me try to understand the question. I mean, is the question whether I've seen classes of matrices where the leverage scores are uniform to begin with? No, if they are similar to each other. So in genetics matrices, what we see, and I can talk about these matrices because we've done a lot of experiments with many different data sets, they are not similar. There are always outliers, but they don't always appear in the same locations, if that's what you're asking. So we cannot use one matrix to infer something about another matrix. Okay? So at least in those data. The other data set where I've done a lot of experiments is a data from electronic circuit testing, where you're basically given features for electronic circuits. You want to figure out which features clearly determine if the circuit is functional or not. Again, depending on the data set, sometimes depending on the company and the time of the year, if you want, that they are doing the manufacturing, you get very different features to pop out. So I don't think it's that easy to come up with some general rule there.